the whole reason why we make use of derivatives is because, like, if I have a function that represents distance, then when I find the derivative or the slope of a tangent line, I'm finding actually an instantaneous velocity, the velocity at that exact moment, not an average velocity between two time points. But essentially, I'm finding the exact speed or the exact velocity at that exact time. So here when I say find the velocity of an object at t equals 3 seconds. So what I want to do here, if I use the first definition of a derivative, the f prime of x equals the limit as h approaches 0, so forth and so on. Now, I'm going to replace all the x's with t's because the variable I'm using is t. When I do it this way, I'm going to find a formula that would calculate various velocities, and then I'm just going to specifically calculate it at time 3 seconds. So the velocity function, v of t, is going to be the derivative of d of t. So I'm going to do the limit as h approaches 0 of d of t plus h minus d of t all over h. Again, I do my substitutions. Carry this through here. Simplify inside the parentheses. Get rid of the parentheses, more so by allowing the subtraction to be distributed into the second quantity. And again, as my usual thing I want to have happen here is I do want everything on top to have an h, and anything that doesn't have an h, I'm hoping will cancel out with something else that doesn't have an h. And that does happen here. It leaves me with this. And now each one of those has a multiplication of h. I'm going to just divide everything by h, causing the cancellation I would need. Again, anywhere before this point here, if I put 0 into what I had, I would end up with 0 over 0, the indeterminate form, which would also be something that tells me, hey, you got to get some kind of cancellation here to get rid of this. Now, when I evaluate the limit by allowing h to be 0, I get 20 minus 10t minus 5 times 0, so v of t is 20 minus 10t. That is a formula that's going to give me the velocity at a given time t, the instantaneous velocity. So now at this point, I'll just plug 3 in for t and get a negative 10 meters per second. Remember, since velocity is a vector quantity, not a scalar, it's a vector, it has a magnitude and a direction. So if I was to interpret this correctly, negative 10 meters per second means that since it's based off the distance formula I have there, that's a distance a function is from me at a given time. Well, if the velocity is negative, that means that at this given time, this object that's flying, whatever it's doing, is moving towards me at 10 meters per second. Important to know, because if it's moving towards me, I might have to duck. If it's moving away from me, I could say, okay, that's neat, it's moving. So that's what the negative stands for here, because it is a vector quantity. It's just indicating a direction, and that direction in this context means towards me. My other possible way of calculating this was to use the second definition. This would immediately allow me to figure out the velocity at time 3 without coming up with a formula. That comes in handy if I'm not asked to find several different instantaneous velocities. If I'm asked to find several different instantaneous velocities for a situation, then I may want to use the first definition and get a formula for velocity and then use that velocity formula. Here, if I'm only looking for the velocity at time being 3 seconds, then I can use the second definition. So that means that v of 3 is going to be d prime of 3, which equals the limit as t approaches 3 of d of t minus d of 3 all over t minus 3. Some students like to go with this one because there's less usage of foiling and things like that, so they tend not to make as many errors when they start doing their algebra. D of t is just me rewriting the formula 18 plus 20t minus 5t squared. D of 3 is me putting 3 in for all the t's, and of course on the bottom we have t minus 3. So what I end up with when I do some simplification is that I have the limit as t approaches 3 of 18 plus 20t minus 5t squared minus 33. Now we talked briefly about these type of difference quotients way back when, but if you remember, we wanted the t minus 3 on the bottom in this kind of instance to disappear. The reason being, if you actually put 3 in right now, you do get 0 over 0. Which means that that t minus 3, that 3 is a domain restriction for the rational function I have here. And with that being the case, I want this, that indeterminate form to disappear, so I want t minus 3 to be able to cancel out. So as I do my various work with this, with the top, and factor and do everything I need to do with it, I do want to get to a point where t minus 3 does sort of pop out of it. So I look at this at the top, I get, I do some rearranging and simplifying, I get negative 5t squared plus 20t minus 15. I could divide out a negative 5 and get negative 5 times t squared minus 4t plus 3. And t squared minus 4t plus 3 does factor into t minus 1 times t minus 3. So now on top and bottom, I do have a quantity of t minus 3 being multiplied. On the bottom, you don't notice it as much because it's being multiplied. Well, I got ahead of myself. It's being multiplied by 1. So, now I can do the cancellation, which I do show there. Leaves me with v of 3 equaling this. And now that I've caused that cancellation, I should no longer get 0 over 0 when I put 3 in for t. So now I put 3 in for t, I do get the same negative 10 meters per second. So it doesn't matter which one you use. It's just some circumstances you're going to find it's better to have a formula for the velocity for any time. So I can just, if I'm looking for velocity several different times, I can just plug those numbers in and be done. If I'm looking for one at this one specific time, it might be easier just to go cut to the chase and go right there.